All right, good evening, everyone. Welcome to MAPS, Modesto Area's Partners in Science, and our Legacies of the Carboniferous talk. So I just wanted to thank everyone for coming to join us. One of the advantages of joining live is that you will get to type any questions into the chat. We'll be answering questions at the end of the talk. So before we get started, I just wanted to draw your attention down. If you scroll in the information part of the YouTube page, we do have some background information about our speaker tonight and also connections to the Great Valley Museum. You can keep connected to the Great Valley Museum through this YouTube page or Facebook or Instagram. And there's also a link to our MAPS page to tell about talks that are coming up. And just to let you know, our next talk next month in April 16th, is about the some Mars rovers. So that exploring Mars with NASA's Curiosity and Perseverance rovers. Also next month, April 16th, a half an hour before the talk, so at 7, we are going to have a little tribute to Lance Thompson. He's a former dean of the Science, Math, Engineering division here at MJC, and he was very instrumental in helping MAPS get started and a great supporter of MAPS. And so we did want to remember him for that and dedicate the April talk to him. So keep an eye on our webpage for more information on that upcoming talk. And then for as far as other science talks that are coming up, our science colloquium has a couple more talks this semester. Our next one is coming up Wednesday on drones. So that is something to keep an eye on as well. And so I will turn this over right now to Professor David Martin, who is going to introduce our speaker. So thank you, Dave.
All right, thank you, Linda. Well, welcome everyone tonight. We look forward to having you here at this presentation. It's my pleasure to introduce our speaker tonight. It's Dr. H. Edward Clifton. He's a geologist. He was a native of Ohio, and he graduated from Ohio State University. Ed earned his PhD in geology at Johns Hopkins University and immediately joined the U.S. Geologic Survey in Menlo Park, which is on the San Francisco Peninsula. There he resided and worked for 28 years conducting research on coastal rocks and sediments. During this time, he also served as an adjunct professor of geology at Stanford University, National President of the Society for Sedimentary Geology, and for 3 years, Chief of the USGS Pacific Branch of Marine Geology. He became the world's first geologist aquanaut in 1969 as a crew member of the Man in the Sea mission, Techlite 1, in which he and 3 other marine scientists spent 2 continuous months living and working from an undersea habitat. And Techlite 2, which was a 20-day mission in which he served as crew chief. In 1991, he retired from the USGS and took a job as an internal consultant for Conoco Incorporated, interpreting sedimentary rocks from many different parts of the globe. He retired from Conoco in 1999 and moved to the Monterey Peninsula, where he has been a volunteer guide at the Monterey Bay Aquarium, a member of the board of directors of the Pacific Grove Museum of Natural History, and a docent at Point Lobos State Reserve, where he specializes in the geologic history of the reserve. In these capacities, he has received the highest volunteer awards conferred by California State Parks, the Point Lobos Foundation, and the Monterey Bay Aquarium. So it's my great pleasure to introduce to you tonight Ed Clifton, Dr. Ed Clifton, our geologist now in residence. So welcome, Ed.
Well, thank you. I guess I'm coming through. I hope I'm coming through. Yeah, we're going to talk this evening about the legacies of the Carboniferous, a geological period with far-reaching consequences. And I'm going to start with a personal legacy. Excuse me. When I was a kid growing up in northeastern Ohio, I was about 10 or so, and my father joined with a bunch of friends, and they bought a hunting camp in the Allegheny Mountains of western Pennsylvania. It kind of looked like this, not quite this posh, but it was a wonderful place to visit. And I just loved going there, hiking through the woods. And at that time, I had an interest in geology. I'd collected rocks for a long time and loved the stories they told. And my parents bought me books on the subject to try to stimulate my interest. And actually, I found the books kind of turned me off because the things they described were of a scale that just were beyond changes in the earth. It was just beyond anything that I could imagine. Well, one day I was walking along a trail near the cabin and I saw a funny looking rock and I picked it up, and this is it. This is the rock right here. I find, there's the camera. And this was really strange. I knew that this was something that was totally out of place. I thought maybe a piece of petrified palm tree, but something that was totally foreign to the deciduous forests of Western Pennsylvania. And I knew the rocks there were about 300 million years old, something called the Carboniferous Period. And I realized that the world had indeed changed. It brought it home to me. And I think this was a factor when a few years later, I began studies I enrolled at Ohio State University. One of the first things I did was to declare a major in geology. So the Carboniferous, what are we talking about? What is it? Well, it's a time period that it covers about 300 to 360 million years ago. And geologists divide the Earth's history up into 4 big segments called eons, and life is present through most of this time, but life as we know it is really restricted to the last one, the Phanerozoic eon. And the Phanerozoic eon is divided into 3 eras, each with its own set of life forms. So the Paleozoic is characterized by invertebrates, fish, and reptiles, the Mesozoic by dinosaurs, and the Cenozoic by mammals. And each of these eras has a set of periods, and the periods are really the sort of the prime currency of geologic time. And the Carboniferous is one of these periods between 300 and 360 million years. Now, our world today is really a composite of what's happened in the past. It's the result of previous events and previous history and legacies from the past. And every one of these geological periods has its own contributions, its own legacies to the present, but they're not all of uniform scale. For example, probably the most familiar geologic period today is the Jurassic period because of the movies. But the Jurassic, the legacies are, well, the first bird-like creatures appear in the Jurassic. And other than that, and a book and 4 movies, that's about it. And in contrast, the Carboniferous, which is of similar time length, has a whole bunch of legacies that it passes on to us today. It was a remarkable time in the history of the Earth, and its legacies begin with, over the last 4 million years, it's the global climate most like that of today. It is a remarkable period in the evolution of plants, a pivotal period in the evolution of animals, and our oldest identifiable ancestors appear in the Carboniferous. It contributed to an extinction event somewhat later that opened the door to dinosaurs and mammals, and much, much later, it fueled the Industrial Revolution and thereby shaped our modern world. And today, it underpins a threat to human health and well-being. So those are the legacies of the Carboniferous that I'm going to be talking about. And to do this, I'm inviting you to join me on a field trip to the Carboniferous. Bring rain gear, waterproof boots, and oh yeah, a really effective insect repellent. We're going to start, though, not in the Carboniferous, but in the Devonian period, which preceded it. At about 370 million years, the land masses of the Earth were concentrated into 2 giant continents, Laurasia and Gondwana. And for reference, what will later become North America and Western Europe are both on the south side of Laurasia. And the continents are not just sitting there stable. Gondwana is moving to the north towards Laurasia to the point that by the middle Carboniferous, it has reached Laurasia. And by the end of the Carboniferous, it's actually crunched into it, and North America and Western Europe are caught in the bind between those two massive continents. We'll talk more about that later. In North America, the lower or early Carboniferous is mostly shallow sea deposits that extended over much of north of the United States, whereas the latter part is marked by a giant swamp area that extended out from the north and east. And because of this difference, in North America, the Carboniferous is considered two periods, a Pennsylvanian period above, a Mississippian period below. But in this talk, I'm going to stay strictly with the Carboniferous as the term for the whole time span. So why the Carboniferous period? Well, it's a lush green world dominated by plants. And plants have been around for a long, long time. Going back a billion years ago, there were plants in the sea and probably long before that, but they were mostly algae, and they were only in the sea. At that time, the onshore areas were barren. There were no plants at all. But as we move on, about 470 million years ago, the marine plants are getting somewhat specialized, and some of them are starting to move onshore. This might be what the shoreline will look like 460 million years ago. And to make this transition required an evolutionary change because if the plants were just put out there without a waterproof cover, they'd dry out. So the change was a waterproof cover in the form of a wax cuticle that sealed the moisture inside so the plants could live separate from the water. But they had to have something else because being out in the air, they needed to get carbon dioxide from the atmosphere. And to get that into the plant, they had to have openings. So they had little stomatas or pores that could open and close, bringing carbon dioxide when appropriate and closing and sealing the moisture in otherwise. And basically, virtually all plants today have these. Those early plants probably looked like modern day liverwort, which is a plant I don't think I've ever seen, but that's what you would have seen on an Ordovician shoreline. And the plants at that time were really constrained to being in or near the water. They couldn't get away from it because there was no water to be had to splash up on them to keep them moist. And they couldn't move away until they developed the plant vascular system. And a plant vascular system consists of two different kinds of tissue. Xylem, which is made of dead cells, dead plant cells, is watertight, and it acts as a conduit for moving water through the plant by capillary action. The phloem is a different tissue that's made of living plant cells, and it has tiny little perforations that allow the sugar and the water to be redistributed through the whole plant. So a plant just needed roots that it's extended into a moist soil, and then could bring that water up, and the plant could live away from the water. And some of the early plants that did that probably looked a little like this. By the time we get to the Devonian, the plants had really moved onshore. There were trees, there were forests, and so the earth was becoming green. At that time, North America, Europe, China all lay near the equator in what today would be a wet zone. Lots of rainfall. And so the landscape there may have looked a bit like modern day landscapes in our present day wet zone, like this peat swamp in Borneo. And so that may have been kind of how the Carboniferous forest looked, but with very different vegetation. One of the trees that was left over from the Devonian is Archaeopterys, not to be confused with Archaeopteryx, which is a fossil bird-like critter. But Archaeopterys was probably really the first true tree. It had a solid trunk and fern-like leaves, reproduced with spores. And as far as anyone knows, it has no living relatives today. Where there was water, there was a wetland tree called Calamites. And I put the tree here in quotes because Calamites is more of a herb. It's described more as being more of an herb than a tree, although it could get up to 150 feet tall and form fairly thick forests. But the trunks and the branches were hollow, kind of like bamboo. And so wherever there was water, you had a lot of Calamites. And I bet just about all of you who spend much time outside are familiar with its modern day relative, the Horsetail Rush or Equisetum, which lives in damp places today, just like its ancestor did in the Carboniferous. These are plants I've never seen. They're club mosses. They're little evergreen plants that live in the northern parts of North America and Europe. And if you look at the name Lycopodilia, it gives you a clue that these are related to the lycopods, the scale trees, which I think are the iconic trees of the Carboniferous. There were a couple of them that really stood out, Lepidodendron and Cigallaria. They were called scale trees because their bark had the appearance of fish scales or reptile scales. And each one of these was a little leaf scar that they had little grassy leaves sticking out, I think pretty much like the little leaves that are sticking out, or whatever they are, the bristles sticking out from the stems of the modern day plants. Lepidodendrons grew in thick groves. They were a big tree. They could get up to 150 feet tall and more than 6 feet diameter in the trunk. They were kind of a strange tree because the trunk wasn't solid like trees of today, which are solid wood. There was a strong outer trunk, mostly bark, and then inside that was a pithy inner trunk that I suspect you could dig the insides out with a spoon. Very, very soft. The lepidodendrons made really dense groves, and they could do that because of the way they grew. They would shoot up and not branch out until they reached their full height. Then they would branch out, reproduce with spores from things that look like cones, and then they would die. And all of this in about 10 to 15 years. They didn't live very long. So they'd sprout up, die, and then another group would fill the space. And so they could put immense amounts of woody material into the Carboniferous swamps. Another abundant Carboniferous scale tree is Cigallaria. Cigallaria, like the Lepidodendron, had a trunk that was hollow on the inside or filled with pith. And like Lepidodendrons, it would grow up to its full height before branching into 2 branches, and each of which would get a bunch of grassy leaves, sort of looking like a giant bottle brush. One of the really kind of curious things about the scale trees is that they're commonly found in an upright position, as with this stump of a Cigallaria in a cemetery in Great Britain. And the strange thing is that we're not looking at petrified wood here. What we're looking at is a stump that's made of sandstone. And what we're seeing is actually a cast. Fossils can be either in the form of casts, the inside of the shell, or molds, which replicate the outside of the shell. And these are casts of the inside of the tree, made of sandstone. How in the world do you get something like that? Well, I think you can see the answer here, because the trees had this inner core that was really soft and pithy. So when they died, that would just blow away basically or be eaten by insects, and leaving a hollow stump that would be hollow all the way down into the roots. Then if you had a flood, a big flood coming over and depositing sand over this entire area, they would fill with sand. And I think because of the organic matter in the enclosing stump, that sand got more tightly cemented than the rest of the sand. So the rest of the sand could be eroded away, and what would be left is that inner core of the tree. So the tree itself was significantly bigger than the stump that is preserved. And this would extend right down into the roots, which are not really roots, but more like branches that extended out underground. They were also hollow, and they also would get filled with sand. The roots were little rootlets that attached to these stems, and where they broke off, they left little scars. And if that looks kind of familiar, well, that's what we've got here. My sample is the cast of a Cigallaria root that lived in the swamps of Pennsylvania when Pennsylvania lay south of the Earth's equator some 310 to 300 million years ago, 320 million years ago. There were also trees that came in later in the Carboniferous that didn't really they weren't part of the swamps or the rainforest. They were upland trees. And these were early conifers. They had all the characteristics of pine trees. And so the pine forests of today also have Carboniferous roots. And there were animals that lived in these rainforests as well. In the Devonian, fish broke out of the water and started breathing air, developed lungs, breathing air, converting their fins into legs that could move them about. And so we have the first amphibians coming in, appearing on the scene in the Devonian about 380 million years ago. And the amphibians were really common in the Carboniferous. It's commonly called the age of the amphibians. And some of these amphibians weren't to be messed with. Archaeopterys was a late Carboniferous amphibian. It was about 6 feet long, and it had a nasty set of teeth. Presumably, it fed on fish, but my guess is it gobbled up anything that moved in front of it and got in its way. Now, the amphibians, like fish, had a gelatinous coating over their eggs. And if that was taken out of the water, it would dry out and the little embryo would perish. Well, in the Carboniferous, the amphibians were probably laying their eggs higher and higher in the ponds, trying to keep them safe from predatory fish. And if you're putting your eggs high as close to shore as possible, you want the strongest shells. They're the ones that are going to survive. And so you finally get shells that are strong enough, they can be taken completely out of the water. They don't need it. And the little reptile develops, the little embryo develops inside that egg in the water that was put there, and eventually hatches out and is ready to go. And the earliest known reptile comes in late in the Carboniferous period. Hylonomus, about 312 million years ago, was about 8 to 10 inches long. It's the oldest confirmed reptile. And here I have to make a slight digression into vertebrate skulls. There are 3 types depending upon the number of openings behind the eye socket. Anapsid skulls have no openings, and they're represented by amphibians and turtles today. Diapsid skulls have 2 openings, and they are represented today by birds, snakes, crocodiles, lizards, and in the Mesozoic, the dinosaurs. And synapsid skulls with 1 opening today include all the mammals, and that also includes us. So the earliest reptile that we know, Halanomus, had an anapsid skull, which is probably reflecting the fact that it hadn't evolved yet far from the anapsid amphibians. But before the end of the Carboniferous, we have the first known diapsid reptile. And this little reptile, or one of its kind, like it, was going to produce eventually all the birds in the world and the dinosaurs, a whole group. And there were also synapsid reptiles as well in the Carboniferous, several of them in the latter part of the Carboniferous. And one of them, or something very like them, is going to be ultimately our ancestor. So we can trace our ancestry back in terms of specific kinds of animals to these earliest known synapsids. And beyond that, well, there are probably amphibians involved and fish, but we don't really have a clue. But we can take our lineage back to the Carboniferous. Now, some of the pictures look like they've had birds flying around in them. Those are not birds, those are insects. And the insects of the Carboniferous were really big. Dragonflies, excuse me, with a wingspan of 30 inches. There were some big cockroaches too. I don't know how many of you have had the experience I've had living in the South and turning on a light in a room in the middle of the night and watching the water bugs, which is what they euphemistically call cockroaches, scurrying about trying to find a dark corner to hide in. Imagine turning on the kitchen light and seeing roaches the size of bedroom slippers scurrying about your kitchen. And wait a minute, these look like tire tracks. In Carboniferous rocks, are we seeing evidence of ancient aliens and their vehicle? No, we're not. We're seeing two separate tracks of an animal that is about as alien as anything that's lived on this planet. It was a giant millipede or centipede that got up to 8 feet long and several feet across. The biggest invertebrate probably that's ever lived on the planet. And one that I'm just as glad I have never met up while I was doing field work out in the woods. So why'd the insects get so big? Well, insects don't have lungs. They get their air, their oxygen, through a series of tubes called trachea. And these tubes are really tiny and small, and it's just diffusion of the oxygen through. So they only get so much oxygen, and that really restricts their growth. But in the Carboniferous, there was a difference in the atmosphere. It's commonly considered that there were 35% of the atmosphere was oxygen, as composed to 21% today. And with that extra oxygen, that allowed the insects to grow really large. And in fact, the Carboniferous had the highest level of oxygen probably ever in the history of the Earth. So why? Why such a high level of oxygen? You commonly read a statement like this: the growth of these forests remove huge amounts of carbon dioxide from the atmosphere, leading to a surplus of oxygen. Sounds reasonable until you realize that today, carbon dioxide is a trace gas, about 0.04% of the atmosphere. And during the Carboniferous, it was probably even less, given the fact that the plants were drawing it down. And you could convert all of that carbon dioxide, replace it with oxygen, wouldn't really matter much to the oxygen level. So that's not the reason. I think the reason is tied up in the way plants photosynthesize and use and create oxygen. Because they photosynthesize by taking carbon dioxide and water and combining them using the energy of the sun to create sugar. And in the process, they release 6 oxygen molecules. So the process of photosynthesis leads to increased oxygen in the atmosphere. But plants also have to use that sugar to provide energy for growth. And that requires oxygen to be brought in during the process of respiration, typically at night. And so plants both create oxygen, but they also take oxygen out of the environment as well. A study was done in 2001 by an international group studying the oxygen budget of the Earth, concluded that the amount of oxygen that is put into the atmosphere by photosynthesis is balanced by the amount that is removed by respiration, both on land and in the oceans. And so that respiration is not just the plants, that's also the animals. And we animals don't produce any oxygen, we just take it out. So I think that one of the reasons the oxygen level could be so high in the Carboniferous is because there weren't that many animals, and the ones that were there really didn't have much of a high metabolism, basically amphibians. And so I would think that the oxygen level would increase with the increasing terrestrial vegetation back in before the Carboniferous and during the Carboniferous. All that terrestrial vegetation is putting oxygen into the environment, and up to the sort of the end of the Carboniferous, you don't have many animals that are pulling it out. And then the rainforests disappear, we get far less vegetation, there's not as much oxygen produced, and we have an increasing terrestrial faunal respiration. We got a lot more animals that are evolving, animals that use more oxygen. So that draws it back down. So that's my guess, and strictly a guess, as to what's happening. Now, one way that the Carboniferous resembles our world today is glaciation, which is really a very uncommon phenomenon. Continental glaciation occurs in the middle Carboniferous about 360, 320 million years ago, something like that. And then we don't see it again until about 35 million years ago. So there's a great lapse, big long period of time where there is no continental glaciation, but it was there in the Carboniferous. And by the end of the Carboniferous, it extended pretty wide, broadly. But you'll notice there are no land masses in the Northern Hemisphere as there are today. And so today we have both glaciers in Antarctica and during the Pleistocene, glaciers extending down from the north. Now the ice never got to the tropics, never got to the area that we've been talking about where our rainforests were, but they would have an effect there. And that effect comes from the influence on sea level, because the water that is trapped in the ice comes from the sea. And so we would go as we went into a glacial period, it's removing water from the sea to form the ice. Then when the glaciers melt, sea level comes back up as that water is added back to the sea. And so the sea level has fluctuated by 100 to 130 meters repeatedly through the Pleistocene, through the last million years. In the Carboniferous, one of the most common kinds of rock features is something called a cyclopham. And a cyclopham is a repetition of rock types. And characteristically, it goes from marine silt up to a shoreline sand, then some non-marine deposits, river, lake, swamp, coal, and then a flooding surface. The sea comes back in and covers all this up. The water gets deeper, reaches a maximum depth, then starts to shallow upward, and the whole cycle begins all over again. And so we're seeing basically fluctuations of the water depth in which the sediments were deposited at a time of continental glaciation, which is pretty much what we see today with modern day sea level fluctuating at a pretty substantial scale. And the rocks that are produced, there are very few places, as you can see a good section through the rocks that are produced during this time, but one of them is in the sea cliffs at Fort Funston, south of San Francisco. And this is a part of the world that I've spent a lot of time studying. And it occurs during a period of glacial and interglacial episodes, and accordingly, sea level has fluctuated up and down through the depth, through the time that that whole section was being deposited. And if you look at the section, you see a pattern to it where it starts with a marine incursion, and then that goes up into a shoreline sand. We get then some non-marine deposits, and another marine incursion back into deeper water, marine deposits. Then they shallow upwards to shoreline sand, and you get this pattern just repeated over and over and over, going from non-marine deposits to a marine incursion, and then marine up to a shoreline sand, up to non-marine, and then another marine incursion over the top, just repeated over and over again. And as a function of the sea level changes of the Pleistocene due to the glaciation. And that pattern is very, very similar to the pattern of the cyclothems in the Carboniferous. The patterns that we have today, the sea level fluctuations, are linked to the episodes of glaciation. And the cycles that we see are thought by many geologists to reflect cycles in the Earth's orbit, in the tilt of the spin axis, called obliquity, or the orientation of the spin axis through time, called precession. And they're called Malinkovic cycles for Milutin Malinkovic, who was a Serbian mathematician, astronomer, climatologist, geophysicist, civil engineer, and popularizer of science. And he came up with the idea that you had these cycles, and when you compare them, compare the cycles to the actual periods of glaciation, there is a remarkable fit. So could these Malinkovic cycles have been an influence in the Carboniferous on the cyclothems? Well, about 6 years ago, a paper was published by a team that had studied Carboniferous deposits in the Netherlands, and there they had some volcanic deposits in the section that provided them with radiometric dates. And having the radiometric dates constrained the time, and they could divide the cycles up into known numbers of years and compare them with Malinkovic cycles. And the comparison you can see here is remarkable. To my eye, it's almost too remarkable, but that's something else. The one thing that you don't see in the modern day that is present in the Carboniferous cyclothems is coal. And coal is a typical part of a Carboniferous cyclothem. In fact, the Carboniferous is known as the age of coal. So how do you make coal? Well, you have to start by putting a lot of organic matter, a lot of woody material into the sediment. Now today, we have wood-rotting bacteria and fungi that destroy much of that, consume much of that organic matter. So we're not making a lot of coal today. But in the Carboniferous, the fungi and the bacteria had not yet evolved. So all of that carbon that was there went into the sediment. Probably everybody who's done any gardening is familiar with peat, organic rich sediment. And so our coal starts off in the Carboniferous as peat beds. And then with time, pressure, and heat, it is transformed into coal. And this occurs through a series of stages. First stage is called lignite. It burns, but it's very inefficient, lots of impurities to it, and you can still see the remains of the plants. Typically, it's brown. Under more heat and pressure, that will be converted to bituminous or common coal. And this is a coal that I think anybody who my generation certainly remembers as a fuel when they were growing up. And then under tremendous heat and pressure, you get the purest coal, anthracite, which is almost pure carbon, burns with incredibly hot heat, very little in the way of impurities, and is the top kind of coal that you can get. Now, if you take anthracite and put it under the heat and pressure that you find in the upper Earth's mantle, you get another mineral, and it's not black. But diamonds are beyond the scope of this talk. So we need heat and pressure to convert the peat to coal. How do we get that? Well, we have continents that are colliding. North America and Europe are caught in a vice between these two continents, and we go essentially from an area of tropical lowlands to mountains. And these mountains, the core of them, can still be seen in the eastern seaboard of the United States. This is a view from space. Chesapeake Bay is down in the lower right corner. And you can see how contorted these rocks are. These are huge stacks of rocks that are essentially pushed together like an accordion. And the pressures must have been intense. The ridges produced by these stand up today as the Appalachian Mountains, and the Appalachians contain a lot of high quality coal. Coal has been used probably by humans ever since they found it. The oldest confirmed use, documented use, is from a excavated Chinese village at about 1500 BC. The Romans mined coal when they occupied Great Britain. It was one of the products that they incorporated. And there was a lot of coal in Great Britain because it had a lot of Carboniferous rock, either cropping out at the surface or buried a short distance below it. And so coal mining in England, or Great Britain, came on pretty early. And those mines must have been just horrible places to work. And one of the worst parts of them is that many of the adits were so small they could only be worked by children. And I've seen this kind of adit in a coal mine in Spain, and it was really heartbreaking. The mines, because they were low openings, typically had problems with water. They would fill with water. And so the first steam engines in the early 1700s were devised to pump the water out of the coal mines. But steam engines rather took on a lot of other purposes as well. And so through the 1700s, the Industrial Revolution proceeded in Great Britain and really kind of changed the world. One of the things it did was transform transportation of people and goods, because now coal-fired steam engines could move people great distances in relatively short periods of time. And the coal railways in the US developed really quickly. In 1830, this source said there were 23 railway miles, and by 1850, essentially 20 years later, there are more than 9,000 railway lines. So it caught on very quickly. And a lot of this, I think, was focused by the presence of coal, the availability of coal. The United States has a lot of coal reserves in the West, and they're younger, and they're also of much lower quality than the coals that we have in the Appalachians and the interior regions. Now, could this be a legacy of the Carboniferous? My historian friends would probably tell me I should stick to the rocks, but I look at the distribution of Appalachian coal, of Carboniferous coal, and it's in the northern states: Ohio, Pennsylvania, West Virginia, Michigan, the Midwest. And this, I'm sure, pushed industrialization. And certainly you could see the effects on railways. There's a much denser concentration of railways in these northern states than there are the southern states. And the southern states, with far fewer coal resources, remain pretty much an agrarian society with an economy founded on slavery. And so that set the die for the Civil War. I don't know what the world would look like today without the Industrial Revolution. There would probably be a city, San Francisco, but I'll bet it wouldn't look like this. At the end of the Carboniferous, several things happened, or toward the end. First of all, there was a glaciation, there was a collision of the continents, so uplift and colder climates, and that led to the collapse of the rainforest. They disappeared toward the end of the Carboniferous. And we moved on into the next period, which is the Permian period. Permian period is marked by a supercontinent, Pangaea, and the dominant life form were these big sailback lizards, diapsid lizards. And anybody who's had a set of plastic dinosaurs as a kid has probably seen these before, but they're not dinosaurs. They are a synapsid reptile. They are a member of the mammalian family tree. There were other synapsid reptiles that actually started to look a little like mammals during the Permian, but they still laid eggs. They were still reptiles. Geologic history is marked by extinction events where a large number of species disappear. And these are commonly used as markers between the periods, as period boundaries. The Carboniferous doesn't have any really major extinction events. There was one in sort of the middle Carboniferous, which is thought to relate to development of glaciers and is mostly affected the marine fauna. And then the later one, in the later part of the Carboniferous, which impacted the rainforest. When the rainforest disappeared or collapsed, there were a number of terrigenous species that disappeared. But there was nothing like the great extinctions that occurred not too long after that during the Permian, both the result of great extrusions of basalt, large volcanic events. And the second one is the greatest extinction that ever happened. It's called the Great Dying. And in it, at the end of the Permian, 70% of the land species and 96% of the marine species disappeared. So why such a massive kill-off? Well, first of all, it was a huge area that had erupted, so it went on for a fair amount of time. But the other part of this is that it erupted through some Carboniferous coal reserves, coal measures that were really thick. So as it went, it was burning all this coal and releasing carbon dioxide into the atmosphere. This was kind of confirmed in a paper just last year, where a study of some of the coal or the volcanic deposits contain lots of little pieces of partially burned coal. And so lots of carbon dioxide in the atmosphere and acidification of the oceans, which could have caused that massive extinction of the marine species. But life went on and things survived. Some of the synapsid reptiles survived. There's one of them in the circle. That little guy, in maybe 20 million years, its offspring or its descendants will be the first mammals. And looking at it are a couple of dinosaurs, newly arrived on the scene. And they're both of them because of the extinction of other things that had lived before, allowing them to develop. And so the dinosaurs, in a couple tens of millions of years, are going to be the ruling life forms on the planet for another 135 million years. So we talked about Carboniferous deposits fueling the Industrial Revolution, but they also fuel something else that's a threat to our way of life and our health, and that is carbon dioxide. Carbon dioxide is a greenhouse gas, and its abundance in the atmosphere is clearly linked to temperature, as these data from my core, an ice core in Antarctica show. The temperature is derived from an oxygen isotope that's proved a reliable geothermometer, and the carbon dioxide is derived from the analysis of tiny bubbles in the ice. And there is a one-to-one correlation between carbon dioxide and temperature. In the second half of the 20th century, the carbon dioxide level in our atmosphere today started to increase at a rapid rate. And at the same time, so did global temperature. And this raises the point of concern about carbon dioxide and global warming. Now, how coal enters into this is that for the same amount of energy, it emits far more carbon dioxide when it's burned than do any of the petroleum products. In fact, it's about twice as much carbon dioxide is emitted than for natural gas. So it's a big emitter. And in Europe and North America, the production of coal over the last 40, 50 million years has declined. But in the Asian Pacific sector, it's gone up by 4 times. And it's that increase in coal production and usage combined with the carbon dioxide potential emission that is the point of my concern. And the big scary thing is the melting of the Antarctic ice caps and the flooding of all the coastal areas. And this has happened 50 million years ago. It was nearly an ice-free world, and the coastal areas were flooded, a major disruption. But I think that's a long way off. I don't think that's something we're likely to see in the course of any lifetimes or many, many lifetimes. But there's something else that's more immediate. And that is the effect of warming of the ocean on storms. And the damage from storms is not the wind, it's the water that's pushed ashore by the wind that on top of a normal high tide really can flood an area, and the waves then can be absolutely destructive over the top of this. And so we get Katrina in 2005 in New Orleans, 1,833 people killed, $100 billion worth of damage. In 2013, the capital of Leyte province in the Philippines, absolutely destroyed. The water, they said, was as high as a coconut tree. And these storms have killed, in the last 50 years, about 500,000 people, just 3 storms. And again, the issue is flooding. So the storms are generated near the equator, both typhoons in the Pacific and hurricanes in the Atlantic. And there's a clear-cut relationship between the power of the storms and the sea surface temperature. I plotted up the number of magnitude and distribution of magnitude 5 hurricanes in the Atlantic over the past 100 years from 1920 to 2020. What I found was that the first 80 years there were 13 magnitude 5 hurricanes, and the next 20 years, another 13. A study of the strongest hurricanes and typhoons since 1979 indicated that 5 of them were this last decade. And NASA, NOAA are both noting that there is a potential for stronger storms and typhoons. Flooding from high tides in the US has doubled in just 30 years. 50% of New York City is at risk from storm surge, and to protect the city is going to take about $4 billion. And some cities like Miami, there are questions as to whether it can be economically saved or have to be abandoned. But I want to focus here really on Asia. In Asia, they have something called the LECZ, the Low Elevation Coastal Zone. All the land that's less than 10 meters or 30 feet high. And there are hundreds and hundreds of millions of people living in the low elevation coastal zone. And they are all potentially in harm's way from storms that'll arrive by the end of this century. And I think the devastation that is likely to occur is just going to be staggering. But I want to leave on a more positive note and reflect for a minute on the coal reserves that still remain in the ground. And there are lots of them. And that may be a salvation for us sometime in the future. We still live and continue to live in an ice age where there are glacial and interglacial intervals. And we are an ice age creature. We evolved 200,000 to 300,000 years ago. We survived at least 2 glacial stages. And so while we can handle the ups and downs of the climate, there's a question of whether our civilization can. Our civilization developed during a really consistent period of climatic consistency. And some historians think that that was probably a requirement. 15,000 years ago, the world was coming out of one of the deep glacial cycles, and it came out and temperatures got almost back to where they are today, and then the bottom dropped out. And we went into something called the Younger Dryas, right back into glacial conditions. Why? Nobody really has a good answer, but it happened. One of my favorite places is Yellowstone National Park. It's beautiful, and its glaciers or geysers are fueled by a hot spot in the Earth's mantle. And every now and then that hot spot erupts in a mega eruption. The last one left a huge hole in the ground, which is the Yellowstone Caldera. And the amount of ash that's blown out by a Yellowstone mega eruption is tremendous. Some estimates are that 2/3 of the United States would be uninhabitable after a mega eruption. US Geological Survey has said that 3 extremely large explosive eruptions have occurred at Yellowstone in the past 2.1 million years, with a recurrence interval of about 600,000 to 800,000 years. The last one was 640,000 years ago, which means the clock is ticking. And that doesn't mean that we're going to have a mega eruption in the next decade or this century. It may not happen for another 100,000 years, but the potential is there. The point is that stuff happens. Climatic stuff happens. And we don't always know why, and we can't do much about it. But we do have resources that may be available to help us sustain our way through it. So there may yet be another legacy of the Carboniferous that still will come to sustain our civilization through some future unforeseen catastrophe. And with that, I thank you for listening. Anybody awake out there?
Mm-hmm.
Linda?
David, Dan, are you ready with a list of questions that have been coming in?
Yes. So, Dan, do you want to start, or do you want me to?
I'll go ahead and do the first question. This was from the beginning, from Raphael. Was it hard to get into John Hopkins? And a lot of our students would kind of like to know the process of getting into a science program, since we're have a AA degree, so like a bachelor's and a master's and doctorate level.
Well, first of all, you have to recognize that my experience goes back about 60 years to when I got in. And getting into Johns Hopkins in those days may have been very different from today. Getting funding in those days for science was really great because we were in the post-Sputnik era. And there was a lot of money for science. There was a lot of, I went through graduate school, came out without any debt whatsoever. I was sponsored by the NSF for the last 2 years I was there. And it was a really good time to be in school. So I can't really answer the question today about how hard it is to get in because I was there so long ago.
Well, thank you, Ed. Another question came in from, oops, my thing just jumped. I'm sorry, had it all pigged up and it jumped. This one is from Maria, and she'd like to know about the Cigallaria route today. Are there places where you can still find it? Is it rare? And then are there places where you can find Carboniferous fossils today? It's a little later question, but.
Yeah, I think it's probably, I found that piece just walking along a trail. And I'm guessing that there was more of it if I'd really looked around. I've noticed that you can buy them on eBay. My sample would probably run about $30 now, so it's a real investment for me. And but yeah, there are places that Carboniferous fossils. You just need to find the Carboniferous rocks, and if you need for certain kinds of fossils, marine fossils, you'll need some limestones. If you're looking more for the plant fossils. But one of the things I've noticed is it gets harder and harder to collect fossils. Places have tightened up rules as to what you can collect. I've recently learned that you can no longer take any kind of a fossil out of the soil or the rock in Oregon, in the state of Oregon. And that kind of surprised me. I didn't realize it was like that, but it's getting more restrictive. But in California, there are, the Carboniferous deposits we have are so metamorphosed that they are now a totally different kind of rock, and you can find them in the Coast Ranges. But I don't think there are many places you could look in California to find Carboniferous fossils.
Okay.
All right. This question is from Cecilia. Are large insects due to tropical climatic regions?
Say that again, please.
So are like the large insects from that time period due to like tropical climates?
Probably not, because my guess is what we're seeing is most of the rocks that we have that they come from those tropical regions. And I'm sure there are Carboniferous deposits that formed in the southern hemisphere that I don't really know very much about, but they would be more temperate. I would expect the insects there to be essentially as large. It might be different kinds of insects, but I think I think probably you would find the big insects all, wherever it was appropriate for insects to be flying. You'd probably find the big ones in that part of the Carboniferous.
Okay, I have another question from Cecilia. Are today's sea levels a function of glacial and interglacial periods or due to human changes to the atmosphere with pollution?
Um, Great question. And certainly the big changes that we're seeing in the Pleistocene are, they're all due to glacial, interglacial effects. In terms of modern, um, what what's at risk is the melting of the Antarctic ice cap and Greenland, for that matter. And so atmospheric, as we put carbon dioxide, greenhouse gases into the atmosphere and warm the earth, and those areas melt, that's going to change sea level to a fair extent. I was reading something just today that talked about, I think, maybe 8 meters of rise or 20 meters of, if all of the ice on Greenland melted. It was a significant amount. It was an eye-catching amount. And but that's also a slow process. It's not going to happen overnight, but it will, if it progresses in that direction, it'll put coastal cities at serious risk. And you superimpose on top of that the increased storms, and well, the coasts are going to be a hard place to live.
All right, this question is from Joshua, and his was about a little bit about this being a natural, like what we're going through today. Is it a natural or humans causing the global warming? So do you think that Earth could be entering another period of warming in a natural cycle?
No, I don't think so. And the reason I say that is that we are in and have been in the sort of the high end of temperatures through the glacial cycles. If you think about those curves I showed, where the glacial and interglacial periods, our temperatures today are pretty much the same as the top temperatures of the preceding global cycles. And so I don't think we're going to see any significant increase in temperature through natural cycles. We'll see eventually. I think if you look at the temperature over time, there is a slight decline. I think we are in the beginning of a decline going back to an ice age, but that ice age is probably 30,000 years away from us, maybe even 50,000 years. And the rate of decline of the temperature, it's consistent over the past several thousand years, but it is completely offset by the increase of temperature that has transpired from global warming.
Okay, so one last question here, and that's about the Carboniferous fossils again. Where can most of the Carboniferous fossils be found on the Earth today? So basically where are the Carboniferous deposits today?
Oh, you've got so many different kinds. It's difficult to answer because any place you have coal beds, coal measures, the chances are excellent of finding plant remains in those coals. So that would, if you're interested in plants, why, you'd look in the coal areas. If you're interested in seashells, the lower Carboniferous in the United States is lots of limestones, and so there are lots of shells. Vertebrate remains, boy, that would be a hard one. I'm not sure where you would look for vertebrate fossils, but probably, well, you wouldn't look for them in the sea because other than fish, and there were a lot of fish and sharks in the marine environment. So you might find some shark's teeth or things like that in some of the marine deposits. The marine deposits are more present in this country in the West and Midwest. if you remember that one map I showed early on that showed the distribution of the sea in the lower Carboniferous, that covered a big area of essentially the western and midwestern U.S. And so those deposits show up here and there. You'd need a geologic map to find where they were.
Okay. There's a whole bunch of people that have just basically said how wonderful your talk was tonight and to thank you very much, including Professor Gary Hayes. He's our geologist.
Thanks, Gary.
There is, and Terry Curtis, Terry Curtis just retired. She's one of our biology professors. She asked Dr. Clifton, in your conclusion, were you suggesting that we should harvest the Carboniferous coal still available underground in the US?
I would, if I were making the decision, I think my first reaction would be to keep it in the ground and go green. But also recognize that someday you might have to use it. So don't deplete it now. Keep it for something in the future.
Again, thank you, Dr. Clifton. So Linda?
All right, well, I just wanted to thank Dr. Clifton again, and also all of our MAPS committee members for all of our help tonight, and for the great questions from the people who have been attending. We thank you for coming and attending and supporting MAPS, and just to keep your eyes on the MAPS webpage and the Great Valley Museum YouTube page and Facebook page for more information on upcoming events. And I hope that everybody has a wonderful